problem, I have to find the extreme values of this function, the absolute or relative maximums or minimums. So let's do a couple things with this function first. First of all, this is a polynomial. And I know that the domain of this polynomial, as all polynomials, negative infinity to infinity. Those are ugly looking infinities, but they'll have to do. I also know that this function has the highest power is odd, and there is no negative sign in front of the leading coefficient. So I kind of go back to my algebra, and I know that this graph is going to have n behavior that is down, up. It's like the graph of x cubed, the parent function actually of this polynomial here. The graph of x cubed looks like that. It goes down to infinity, negative infinity, and it goes up all the way to infinity. So I want to see, now the graph of x cubed doesn't have any absolute maximums or minimums, or relative maximums or minimums for that matter. It's just a pretty straight, it's increasing the entire way. But let's see if this one does. And I know that my absolute, my maximums and minimums are all going to happen when the derivative either equals 0 or doesn't exist. So let's do y prime, and that would be equal to, well, that looks like it's equal to 3x squared minus 2. So let's set 3x squared minus 2 equal to 0. And I get 3x squared is equal to 2. I get x squared is equal to 2/3. So I get x is equal to plus or minus the square root of 2/3. So making a new graph here, showing my n behavior, I know that I might have maximums or minimums at the square root of 2/3, negative square root of 2/3, and the positive square root of 2/3. And since the derivative is 0, I know that I'm going to have maximums or minimums. Now, one of the things about the derivative being 0, if we take, for example, the graph of x cubed, let's look at the graph of x cubed. We know it goes up pretty steeply, and then as it gets close to 0, it starts to flatten out. And right at 0, actually, the derivative is 0, and then it goes up again. But at no place in the graph of x cubed is there a maximum or minimum. There's an instant right there at 0, 0, where the derivative is 0, where it's flat, but then it keeps going up again. Now, in this particular case, I know that that's impossible, because if it were to just to be flat like that, it would mean that my graph would be going up, because I know it has to be going up because the end behavior is down, so my graph is going up, and then at negative 2/3, if it was flat, it would have to stay flat all the way until I got over here to positive 2/3, and then keep going up, in order for there not to be a minimum or a maximum. So the graph actually has to make some kind of a turn here. I don't know exactly where. And it has to make a turn here in order to have the proper end behavior that I'm expecting out of this graph. There is no way that this graph can stay straight all this time here, because the derivative of that line would be 0. And that would mean that every single point between negative 2/3 and positive 2/3 would have to have a derivative of 0. But I know that the only points that do have a derivative of 0 are plus and minus square root of 2/3. So we're doing a little bit of detective work here that's actually going to enable us to avoid a lot of really messy arithmetic, especially since we can't use our calculator on this problem. So just following this logic, I know that I'm going to have an absolute maximum, or a relative maximum at the x value negative square root of 2/3 something. And I'm going to have, this is going to be a relative max, REL max. And I'm going to have a relative min at radical 2/3 some kind of y value. Now, I could figure out that y value by plugging that radical 2/3 into this equation. But I got to tell you, that is very messy. I tried it several times, I messed up, and I eventually ended up sending an email to the author of the book and said, hey, like, how can I do this problem without a calculator? It's too messy. And he wrote back and he said, you're right, it's really pretty messy. Of course it can be done. And I know that it can be done. It's rather tedious. But he said, some people like their students to be able to do that, but for the most part, it was a mistake. And he hoped he didn't spend a lot of time on this problem number 20 trying to calculate it by hand. But by doing it this way, understanding the graph, understanding that the derivative equals 0 only at these points right here, we can actually identify at least the x values where those turning points are going to be, where those maximums or minimums are going to be, without having to do a lot of messy arithmetic.